Let's talk about one of the coolest and honestly most elegant ideas in all of machine learning, kernels. It's this super clever trick that lets simple models solve some incredibly complex problems. And it all comes down to, well, drawing smarter lines. Let's dive in and see how it works.
Okay, so imagine someone hands you this data set. The job seems easy enough, just separate the blue circles from the red crosses. But you can see the problem right away, can't you? There's just no way a single straight line is going to cut it. The data is all mixed up. So what do? Well, one of the old school ways to tackle this was to start creating new, way more complicated features. You take your basic features and you start squaring them, cubing them, multiplying them together, you get the idea. But this has a huge flaw. It becomes a computational nightmare, really, really slow. And maybe even worse, you're pretty much just guessing which of these new features are even the right ones to use. Which kind of leads you to the big question, right? There has to be a smarter way to do this. Is there a better, maybe more intuitive choice of features we could create to actually solve this problem? So let's try something totally different. Forget all that complicated math for a second. What if we just picked a few points on our graph? We'll call them landmarks. And from here, we can create brand new features based on a really simple idea. For any other point, how close is it to each one of our landmarks? And this whole idea of measuring proximity, well, that has a name. It's called a kernel. And at its heart, a kernel is just a similarity function. That's it. It just tells us how close or similar some point x is to one of our landmarks, like L1. The specific function we're going to use here is a really common one called the Gaussian kernel. Now, I know the formula might look a little intense at first glance, but the concept behind it is actually super simple. That little part in the middle, the ix minus L1 squared, that's literally just the squared distance between our data point x and our landmark L1. So here's what it all boils down to. If your point x is sitting right on top of a landmark, the distance is basically 0, and the whole formula spits out a value really close to 1. But if that point is super far away, the distance is huge, and the formula gives you a value really close to 0. And that's it. Our new feature, f1, is just a proximity score from 0 to 1. And this is a fantastic way to visualize what that function is doing. You can imagine that each landmark creates this kind of hill or zone of influence. Right at the center, where the landmark is, the feature value is at its peak, a 1. And as you move away from it in any direction, the value just smoothly slides down that hill towards 0. And what's really cool is we can control the shape of this hill. We use that sigma² parameter from the formula. If you pick a small sigma, you get a really steep, narrow peak. That means a landmark's influence is super localized. But if you pick a large sigma, you get a wide, gradual slope, meaning its influence spreads out much further. So how does our algorithm actually use these new features? Well, it does what it always does. It learns some weights, we call them thetas, for each new feature we created. Then it just plugs them into this simple equation. If the final number is 0 or more, it predicts class 1. If not, it predicts the other class. Easy as that? Okay, let's just walk through a quick example. Take a look at this point right here. It's super close to our landmark L1, but it's really far from L2 and L3. That means its feature value, f1, is going to be almost 1, while f2 and f3 are going to be almost 0. So if our model has learned these particular weights, the math is pretty simple. We get negative 0.5 plus 1, which is 0.5. And since that's bigger than 0, the model says, yep, that's a positive 1. And when we apply this logic across the entire graph for every single point, this is what you get. The model essentially learns that any point near landmark 1 or landmark 2 is positive. And what that creates is this beautiful, complex, nonlinear boundary that perfectly separates our two classes. We've actually solved the problem we started with. So why is this such a big deal? Well, because kernels give us this incredibly powerful but also really elegant way to create useful new features, and it's all based on the simple idea of similarity. This technique lets even fairly basic algorithms learn these highly complex boundaries, solving problems that looked almost impossible at first. Of course, this amazing technique brings up a couple of big new questions, doesn't it? For one, how in the world do we choose where to put those landmarks in the first place? And two, is this Gaussian kernel the only similarity function we can use, or are there others? And those, well, those are the next steps on the journey to really mastering this powerful tool.